This is Physics 2212, Lab 3, the magnetic field of a bar magnet. So a little introduction here. The purpose of this lab was measure the distance dependence of a magnetic field due to a small bar magnet, simulate that using VPython, and then compare the experimental and simulated magnetic fields. And our results preview, the magnitude of the field decreases as the distance increases, and then we have our magnetic dipole moment of the bar magnet, and then the experimental and simulated off-axis magnetic fields, which are a little bit different. So the main physics concept we need to know here is the Biot-Savart law, which relates the magnetic field at an observation point from a source to the current within that source and the distance between the source and the observation point, as seen in this equation here. And then the magnetic field due to a magnetic dipole can be found by this equation, which is a lot more accurate. And yeah, so a few other important equations to know. An on-axis magnetic dipole creates a magnetic field equal to mu naught over 4 pi times 2 mu over the magnitude of the radius cubed. And then the distance dependence of a bar magnet can be found by k times the radius to the n power, where k and n are constants. So our visual model here, in this box, we have the magnetometer, and then we have our bar magnet, which we're treating as a magnetic dipole, as a surrounding, our magnetic dipole moment here, and then these blue lines indicate the magnetic field, how it curls out from the north and then into the south, like such. So our procedure here, we orient the phone such that the magnetometer app has an exponent of 0. So we orient it with the Earth's magnetic field, and then find the chip, which up here, and then find the distances for the following x components, and then right here, and then measure the on-axis distance for an exponent of 100 microteslas. Record the y component of Earth's magnetic field so we can find the y component of the magnet when we create a 45-degree angle like such here. So our data that we got written down here, all this cool stuff that we did, and then how we calculated the off-axis field using math in this sheet. Yeah, so we can use the regression line equation from the previous slide right here, where the slope of the regression line is n, and the y-intercept is natural log of k, and r is the radius. And then we can set these up so that it becomes k times r to the n equals the magnetic dipole moment of a bar magnet that's like on axis, which is mu naught over 4 pi times 2 mu over r cubed. So by that we can find the dipole moment, and then some observations we made. When the magnetometer is far away, it measures a near zero magnetic field in the x direction, and then as it moves closer to the magnet, the x component of the magnetic field increases. So this is the calculated dipole moment, 1.495, and then we have our constants here, our function to find the magnetic field, and then we have our field arrows that we initialized here, and then we scaled them based on our scale here, and so we can show them as a magnetic field visualization. And then we have our off-axis field, which we calculated here, and then use an arrow to show that in the visualization. So we have here, this is our bar magnet, and this is the magnetic field. See, it's going out through the north, kind of curls back and then into the south. This is where our magnetometer is, and then this pink arrow shows the direction of the magnetic field at that location. So, and then we have our calculations here, the distance, and then the magnetic field at that location. So the results here, as distance between the magnetometer and observation point increases, magnetic of the magnitude field decreases. Magnetic dipole moment is 1.5 approximately ampere meter squared, and then the experimental and simulated magnitude of the off-axis magnetic field, about an 85% difference, so pretty massive. And then our sources of error possible, like other external magnetic fields, inconsistent distance measurements, uneven surfaces, and magnetometer measure error. Plenty of other stuff that could have happened. And then if we hadn't oriented the experiment to compensate for magnetic north, the magnetic fields would differ because magnetic north would contribute to the x and y components of the magnetic field rather than just the y component. Z component would not change because it's a flat surface. If it wasn't, it would change, but let's not worry about that. And then if we were to stick two identical magnets together, the magnitude of the magnetic field would increase because it's two magnets instead of one. Magnitude would approximately double. However, you would need to do more experiments to actually determine that. And then the measured distances for each magnitude of magnetic field would decrease because the total magnetic field magnitude of the two magnets is greater than just one magnet.